It's a pleasure to be here to present our broadband IR emitter chips. Just a little thing, we are 4K MEMS. We are based in Switzerland. We are a fabless business-to-business company developing novel MEMS emitters. So what I want to show you today is what we call our thermal light emitting devices, our TLED. We call them that because they're very small and they resemble a lot what an actual LED looks like. This is a Eurocent, and this is one of our fully packaged chips. It's 1.4 times 1.4 millimeters in size. If we zoom in, we see our hot plate glowing brightly here. It's at 2100 Kelvin, sitting in a vacuum package. And we do all this, the packaging, the MEMS at a wafer scale. So this is a completed wafer. We're looking at the backside. These are the little chips which we can pop out and mount completely on a PCB. So how does this work? A standard thermal light source, MEMS thermal light source, basically has a high emissivity layer sitting on a suspended membrane, and there's generally a resistive heater on this membrane. This heater gets hot and the high emissivity layer glows and everything's very nice, but it generally works up to temperatures of about 1000 Kelvin. Our principle is different. We start with a continuous membrane, all of the same material. In this case, it's tungsten, and it's suspended by these resistive heater springs. We put current through the springs get very, very hot, and the heat is transmitted to the membrane, which then loses it through radiation. So the nice thing about this is we get a very uniform temperature of the membrane. And as we heat it up to 2000 Kelvin, the membrane gets bigger, and the springs allow this expansion by simple rotation. So this gives us a very stable plate. There's no buckling going on, very uniform temperature. Obviously, it needs a vacuum. We're making it this way. We have a through glass via where we bring the electricity up the MEMS layer. We then have a capping layer with a getter, all under vacuum. We put this together on a wafer level process, and it turns into something like this. We've been working on it for a few years now. Back in 2021, we managed to get the MEMS devices working in a probe station. This gives us first light. It showed that our emitters were stable and bright. Then we moved to surface-mounted packages. These were very nice demonstrators, but they're very expensive and not scalable at all. So towards the end of last year, we managed our first chip-scale packaging. And what's really nice about this is we can move from dicing to PCB. This is one just simply soldered directly onto PCB. This one is on, this one is off. We can put them on flex. And as you see here, we just don't necessarily have one emitter. We can actually have 4 emitters here. So if we look at device characteristics, as you've seen, they're very small. The emitting diameter is about 160 to 30 microns. So we can have multiple emitters. They're very flat. The bowing is less than 5 microns, and they're very uniform, which means the temperature across these emitting areas is about plus or minus 5K. These characteristics make it really nice for optics because we have a flat, small emitting surface. We can even include micro lenses. As I'll show, they're relatively fast for thermal emitters. We have a broadband spectrum out to 5 microns. We are talking mid-IR here. And of course, there's a wide range of analysis, as we all know, for these wavelengths. I repeat, the fabrication is compatible with standard MEMS foundry process, and we have wafer level manufacturing packaging, so which means that at high volumes, we can make these guys really cheaply, which is really interesting for opening up consumer and eventually automotive markets. This is how the devices perform. This is showing what happens as we change temperature. Our voltage, the devices get very hot. We go up to about 3400 Kelvin. We generally operate at 2100 Kelvin, which is slightly below 1 volt. Here you can see the device glowing nicely, and this is the spectrum. This is with the glass window. It's peaking about 1.2. When you put a silicon window on, we get out a nice emission out to 5 microns. As I said, the devices are relatively fast. This is showing the on-off time measured with silicon detector in red and indium antinomide detector from Hamamatsu at 4.2 microns. So you can see the response time. And we compared this with the main competitors. We won't name them, obviously. And we see we're considerably faster. We have a 100 hertz 3 dB point. We said we could add optics to this, and this is very nice. We can put, if you put a silicon layer on top of it, due to the high refractive index, we can collect light with very high efficiency and then beam it using a filter, or we're using a lens. And micro lenses can be made on wafer scale, so can filters. So we decided to show what we could do this with a project organized on the fabulous pilot line. Focuslight made the micro lenses, Viavi made the pixelated filters, CSCM blew them in place and measured them. We made and test the system. So what we have here is we have our emitters, this silicon chip on top of it with our 4.2 micron filter micro lenses and the 3.585 micro lenses, filter and lenses. So if we're going to do gas sensing, which we're interested in, generally what one does is has a broadband emitter, and we have 2 detectors where we have a on-band and off-band filter for the gas absorption. This is pretty standard. It assumes that the changes in detector response is less than change of the emitter ages. But because we're very hot and because we can integrate things onto detectors, we thought we would do things differently. So we got our module with our 2 emitters and we put a single silicon detector behind it. And now we can take the ratio of these 2 emitters without the filter, using basically stray light on the silicon detector. And because silicon is so sensitive, we don't need much light to get this done. And then we do time division multiplexing. We turn one on and one off, and then look at what's happening on the detector. We set this up with a standard 40 millimeter path length reflector to concentrate the light. We use a piezoelectric detector with no filter onto it. And we simply stuck the silicon photodiode here. It's just taking light leaking out from the side, which works well because silicon is so sensitive. So what we get is we have our 2 emitters. So we have the signal coming from a reference emitter measured by silicon and the IR signal coming from the reference emitter. And then we can compare that with the signal coming from the device, which is at 4.2 microns. And so what we see here, over time, we have a chamber where the CO2 concentration is changing. We can then back calibrate that because we took the chamber and we put 2 Sensorion detectors into it to give us a background signal. We looked how the CO2 changes in time. We can use that as a calibration curve. We can compare it with our emitters, and then we can look at the residuals. And when we do that and we look at the difference between what we're getting from the Sensorion, albeit photoacoustic detectors, we see a very similar response. So we can get down to the 10 to 20 ppm range. What's interesting about this concept is that we are removing one detector and we're making our cheap emitters and filters together. We went one stage further. We decided what can we do with a really, really small emitter? And we said we can make a really, really small NDIR gas sensor. So we call it the 4K pill. This is here. This is in comparison to the smallest commercial NDIR sensor we could find on the market. Inside is our emitter, 2 detectors, 2 filters, readout electronics. And we get performance similar to standard NDIR systems. We can even extend this within the same form factor to multiple gases with minor increase in size. The design inside, I can't show you its unique optical design. We're actually submitting the patent on it tomorrow. But our goal was to show something which looked small enough to go into a smartphone, because people are interested in analyzing glasses around us when we're sleeping, for example. And so it's interesting to be able to go towards this. We have a single device. This is what we make. We're trying to address different markets, from illumination systems, embedded spectroscopic, the gas sensors, as I showed, and calibration sources. So to summarize, we have these emitters, which are much smaller than everything else. We can integrate microlenses and filters. We're targeting high volume applications, not feasible using existing solutions. And to finish, we can supply broadband IR emitters for evaluation and test, and we're looking for partners in detectors, filters, and also for novel gas sensing applications. Thank you for your time.